So we'll talk about significant figures in measurement. So here's the general idea behind significant figures. Let's say you go to the grocery store, okay? And you go to the produce section, and they sell potatoes in these bags, right? That's a terrible. And what the bag might say something like 5 pounds. Okay. Now, if you were to put this potato bag on a scale, will it be exactly 5 pounds? No, right? You expect it to be around 5 pounds, but it might be a little bit more. It might be 5.1 or 5.2, maybe even 4.9 or something like that. And if it was 4.9 pounds, I don't think anybody, you take it home, you put it on the scale, and it turns out 4.9 pounds. Would you get angry and take it back to the store and return it and say, you're lying to me, or, so you buy a bag of potatoes and it says 5 pounds, but in your mind, you're not expecting it to be exactly 5 pounds. This is a measurement, but it's an approximation. Okay? So, let's say you have, I don't know, some kind of bicycle rack or something. You're going grocery shopping on your bicycle. But the bicycle, or the basket, you got a basket in the front, and it says, we have a maximum weight limit of, let's say, 6 pounds. Okay, you put something more than 6 pounds, you're going to break your bicycle rack or something like that. Okay. Well, let's say you decide to buy, a box of crackers or something like that. And this thing says 1 pound, 16 ounces, okay, so which is equivalent to 1 pound. All right. How much total do we have? What would you guys say? Yeah, about 6 pounds, right? Let's say you decide to buy 1 carrot, okay? This is the carrot here, okay? And the carrot is 0.12 pounds. Okay, so you measured this on a scale, and you wanted to and this turns out to be 0.12 pounds. Okay, so how much is the total weight now? So all three of our items together: the 5 pound bag of potatoes, the 1 pound box of crackers, and the 0.12 pound carrot. Okay, so you want to say, okay, we want to say 6.12 pounds, because that would make sense because we're adding all of these up. But if we put it on a scale, would we get 6.12 pounds? No, why not? Because this 5 pound bag of potatoes isn't exactly 5, this is not 5.00 pounds, right? Okay, it's just something around 5 pounds. So if this bag of potatoes was, let's say, 4.9 pounds, and let's say this was exactly 1 pound cracker box, and this was 0.12 pounds. If this was actually 4.9 pounds, then everything would add up to what? something less than 6.12. It would be 6.02. Or if the bag of potatoes was 5.2 pounds, or if we had an accurate scale and it turned out to be 5.23 pounds, then when we add it up, we're not going to get 6.12 either, okay? And the thing is when you buy the bag of potatoes and it says 5 pounds, we don't know what we're getting. We don't know if we're getting 4.8, or 4.9, or 5.2, or 5.1. We're just expecting something around 5 pounds. We don't know exactly how much. So even if when you add little things like a carrot or something, even if they're precisely measured, when you add it to something with a lot of uncertainty, the final weight that you have, you can't be certain about, okay? And so our best guess, the true answer we should say, okay, is the total weight is 6 pounds, okay? Meaning it, and significant to 1 digit. So this is the general idea behind significant figures, is that whatever is the most uncertain item, in our case the bag of potatoes, you cannot have things more precise than that measure of uncertainty. Okay? So you could say, oh, I'm only adding just this or whatever. We're not sure how much the total is going to be because the potatoes is most uncertain. Does that concept make sense? Okay, and so there's a bunch of rules that I'm going to have to teach you over. We're going to spend pretty much the whole day going over all of these rules, but that's the general idea. You've got something uncertain, and even if you have things more precise, when you do the calculations and you add them together, or you do multiplication, or you do all of these other things to it, your final answer cannot be more precise than the thing that you are most uncertain about. So I guess the ultimate rule is your final answer Oh, here's another practical example, okay? Let's say you're planning on going on vacation, okay? And let's say you're gonna go, I don't know, you're gonna drive to San Francisco, or I don't know, and you can look at the GPS, and the GPS says the road trip is going to take 6 hours and 23 minutes, okay? And it's not super accurate, but you can say, okay, well, it should be around 6 to 7 hours of driving, okay? Now, let's say your friend asks you, oh, well, how long are you going to be away, okay? If you're not sure how many nights you're going to stay in San Francisco, okay, you can say, oh, well, I'm going to, I haven't decided. Maybe I'll stay there for 3 nights, maybe for 4 nights, okay? Maybe I'll be there for 3 days or 4 days. It doesn't make sense to tell your friend, well, it takes me 6 to 7 hours to get there and 6 to 7 hours back, so that's going to be about, let's say, 12 to 14 hours of driving. It doesn't make sense to tell your friend, well, I'm going to be gone for anywhere, between 3 days and 13 hours and 6 days and 13, or, however, 4 days and 13 hours or something. Okay, it doesn't really make, it's best to just say, oh, I'll be gone, somewhere between 3 and 4 days or something like that. Okay? It doesn't make sense to add on extra precision if this big thing over here has a lot of uncertainty. Okay? Or somebody could ask, how much does that house cost? Okay? And maybe you don't know the exact number. You're just going to say, oh, it's probably, let's say you pass a mansion or something, and it says, listing price was $1.56 million or something. Okay? You say, oh, how much is that house worth over there? Well, and then you'd say, okay, well, the listing price was 1.56 million. Okay, what if I add this PlayStation and say, if you buy the house, you get a free PlayStation? Is that is the house now worth $1.56 million and $400? It doesn't make sense to add on these little units of extra precision if there's just a big uncertainty over here. Okay? And so that's what we have with significant figures. And a lot of times when we do measurements in the lab or measurements wherever else, we get into this mindset of everything has to be as precise as it can possibly be. And that is good. We want to be accurate. We want to be precise. But sometimes we forget, this big machine over here is unable to get any more precise than a certain thing. And so everything else that comes after that cannot be more precise than whatever this big machine was that was had a lot of imprecision. Okay, and this so big idea behind significant figures and measurement. Let me just say this. What is this? May is the idea of the propagation of error, or propagation of uncertainty. Okay. If something is uncertain in the beginning, everything after that will also be uncertain, okay? If you introduce a big amount of error or uncertainty somewhere along in the beginning, everything after is going to also have to deal with that amount of uncertainty. Or I should just say, if anywhere in the process you introduce some uncertainty, even if all of the other elements have a lot of precision and accuracy, that large thing of uncertainty is going to kind of taint everything else. Okay, so if uncertainty it quote-unquote ruins the precision or accuracy of the other steps. So sometimes, depending on the place, if something goes wrong early on in a manufacturing process or whatever it might be, they might say, okay, we just have to scrap this because we can't afford to go on and have this thing being uncertain. So that could be a bad thing. Okay. All right. So. So when we talk about maybe we'll talk about taking measurements in the beginning, and it sounds silly because I'm going to show you how to use a ruler, but I think it's a good exercise here. Okay, so let's. Can you guys see this?
Yes.
All right, so the question is, so here is a ruler, centimeter ruler with little tick marks indicating the millimeters. And the question is, how long is the blue bar? And I've done my best to line up the edge of the blue bar to the 0 on the ruler. Okay. And so you, I don't know. Can I zoom in? Here, I'll zoom in right here. Okay, this is the part in question here.
Oh, 7 something. 7.
Yeah. Okay. So we want to be as precise as we can.
7.4.
More than 7. Yeah.
7.0.
Okay, so let's look, right? So each tick mark is what? 0.1, right? So this is 8 centimeters, this is 7 centimeters, and this would be, this line right here represents 7.1 centimeters, this would be 7.2 centimeters, 7.3, 7.4, 7.5 centimeters. Can we all see that? If we look here, though, this is not exactly at 7.1, and it's not exactly at 7.0 either. Okay? So we have a number that's something between, where's my little, do I have a pen tool? Oh, here we go. Okay. So looking at here, it's somewhere between 7.0 and 7.1, okay? So we are certain that it's more than 7.0. We're also certain that it's less than 7.1. And at this point, we just kind of have to eyeball or guess or estimate the last thing that we want, okay? And so looking at this, I would say 7.04, 7.03, and I'm sure if we asked around the classroom, we'd get something similar to that, but not exactly, okay? So the last digit is estimated. And so you could say 7.03, that's probably fine, or 7.04, also probably fine, okay? But it would not make sense. You don't say 7.032165, okay? That doesn't make sense, right? Because there's no way you would know this, okay? But you do know it's more than 7.0, less than 7.1, and if we had to guess, maybe 7.04, 7.03, something around there, okay? And again, this is measured in centimeters, right? So we have 7.03 centimeters. This would be our final measurement. Does that make sense to everyone? Okay, let's zoom back out. Oops. How do I do this? I didn't want that. Something happened. Oh, I broke it. Okay, hang on a second. Output to okay. Is this? I think we're still